Hello, and today we are going to talk about linear regression. So, as I go over linear regression, I'm just going to warn you it's fairly similar, if not almost exactly the same, at least in terms of equations, very similar to what you might remember as slope, the rise over run, y equals mx plus b. The only difference is that we're using linear regression to predict, and the letters that we use for y equals mx plus b are ever so slightly different. But essentially, linear regression is used to predict things. But first, before we get into the details of linear regression, I need to let you guys know that linear regression is actually very closely related to correlation. So before we get into that, first, just to kind of reiterate, here's a couple of scatter plots, and these are depictions of a linear relationship that is measured through correlation. So positive or negative. So on the left, with that straight line, we have a positive correlation because it is going up, left to right, it is going upwards. And I would say that the approximate strength of that is quite strong. That looks like R equals 1.0 because every point is directly on that line. So that is a positive, strong correlation. This, it appears, you'll see this regression line here, the line of best fit, it's kind of sloping in a negative direction slightly. So I would say that is a negative correlation. And the approximate strength, I would say, is weak. Maybe it's like R equals negative 0.1 or thereabouts. But approximately, that would be the strength of this right scatter plot on the right. Okay, so as we mentioned before in the correlation video, and as we know about correlation, it cannot determine causation. It can't determine causality. So if the relationship between two variables has a correlation, we're not saying that one variable is causing the change in the other. Can you stop, helicopters? Anyway, so let's say that we have a correlation between your happiness and the number of Big Macs you consume in a week. And let's say that this correlation is strong and it's negative. It's R equals, and I kind of went to the next line, but that's R equals negative 0.53. Well, that is saying that as your happiness level increases, your Big Mac consumption decreases, or it tends to do so, or vice versa, as your Big Mac consumption increases, your happiness levels tend to decrease. That's what the negative of the negative Pearson's R is telling us. And that 0.53 is saying that it's, they're varying relatively strong together. So they kind of tend to rise and fall at a relatively equal rate. So that's what that Pearson's R is telling us. But we cannot say that, oh, the more Big Macs you eat, the less happy you will be. That's implying causation. Or eating more Big Macs causes you to be unhappy, or you're happy because you do not eat a lot of Big Macs. We cannot make these claims with causation, or with correlation, excuse me. We can't make claims of causation with correlation. One thing that I want to mention about correlation is that there's always the presence of confound variables, also known as third variables. But when you have correlation, you see the strength between two variables, but you can't determine if the changes that are occurring in one is solely because of the other that you're measuring. So let's take, for example, the Big Macs and happiness. The more Big Macs you consume, the less likely it is that your happiness level will be high. So more Big Macs likely to have lower happiness levels. However, there's a lot of different factors that contribute to happiness, and there's a lot of different factors that contribute to people eating Big Macs in a week. And not all of them are solely, the reason why I'm eating more Big Macs is because I'm unhappy. It doesn't make sense. There's way more variables involved. The reason why people may eat more Big Macs in a week, some confound variables of this correlation is, well, one reason why people might eat more Big Macs is because maybe they don't know how to cook. Maybe they don't have very high income, so they don't have enough money to purchase groceries and do more at-home cooking because that can be expensive. Another thing, maybe different variables, confound variables that contribute to happiness or unhappiness could be your income again, your stress level, your relationship status, your whether or not you're in a motherfucking quarantine for during a pandemic. You know, there's a lot of things that contribute to the happiness variable and a lot of things that contribute to the Big Mac consumption variable. So to say that, oh, eating more Big Macs causes you to be unhappy is essentially throwing away everything else that could contribute to unhappiness, which is ridiculous because some people might not have ever eaten at McDonald's, but they still have happiness or unhappiness levels that are being, you know, affected. So correlation has these confound variables, and that's why that's part of the reason why we can't apply causation, because how do we know it's only Big Mac consumption that's contributing to unhappiness or to happiness? So to say, oh, eating more Big Macs causes you to be unhappy, well, no, you can't determine that from correlation. And two, it could be because their income levels aren't very high. You know, they could be unhappy because they can't afford their food, or they can't afford rent, or they can't afford just simple pleasures in life. They could be unhappy because they're going through a lot of stress. They could be unhappy because, again, COVID-19's taken over. So there's a lot of different reasons, and the presence of confound variables, it's important to know about correlation. They're always there regardless of what your correlation is. Now, let's talk about linear regression. So the key with linear regression is that it's used to predict the values of one variable, which will be our y, it's represented by y, with the values of another, which is represented by x. So x is essentially predicting y. X comes before y, we're using x to predict y. So boom. So with linear regression, we're essentially just, again, trying to predict the values of y using the values of x. So we have two sets of variables, like I mentioned, with x and y. Your predictor variable, which is the x, these values are known to us. When we deal with problems of linear regression, oftentimes when we're used to predict it, we will be given the x value and be asked to use this value to predict our y value. So it makes sense that the x variable is known as the predictor variable. The criterion variable is just y. This is what is being predicted. This is what's being calculated through our linear regression equation. So these are unknown to us because we're using x to predict them. And we're using x to give us values for y. So the regression line, I mentioned at the beginning of this video that the regression line, the line we use to calculate linear regression is very similar. The formula we use to predict y using x is very similar to rise over run, to the slope formula, y equals mx plus b, except for this, it's slightly different. Instead of y equals mx plus b, it's y equals bx plus a. It's a little different, but essentially it's the same stuff. So this regression line provides us the best fit for the sum of squares. This is known as the sum of square distances of data points from a straight line. So when we have that linear regression line, which you've seen in scatter plots, you've seen in the plots that the closer that the data points are to that line that's drawn on the scatter plot, the more like the stronger the correlation. Well, that line is just using the smallest sum of squares value. So this is just giving us a line that is as close to all data points as possible, which I briefly touched on in the correlation video. But the regression line is just a line that's drawn in a scatter plot of all plotted points. And this line is just as close to all of these as possible. So yeah, it's just using the smallest sum of squares value, sum of the squared distances. So looking at this formula, the y equals bx plus a, we know that y represents the criterion variable, the variable that is to be predicted. This is what we do not know at this point. And we're using the rest of the equation, hence y equals da 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 da. We're using the rest of the equation to tell us what y is, what the predicted y value will be. X is the value that we plot for the predicted variable. Again, we're provided with X in a linear regression problem. We're saying, oh, x equals 7 and what's y equal? How do you, what's the predicted value for y when x equals 7 or what have you? And we need to calculate that. However, to do that, we will also need to know b and a. So b is the slope of the line, where slope is equal to the change in y divided by the change in x. And then a is the y-intercept, where the line crosses the y-axis. So this might sound very similar to, I think it's algebra, where we have that y equals mx plus b, except again, it's y equals bx plus a. All the same stuff though, just different letters to formulate it. And obviously, little different in terms of the, we're using things to predict. It's linear regression, it's not just slope. So calculating linear regression by hand. Step 1, we have to do our preliminary calculations. Essentially, this is giving us a lot of the same stuff that we did for Pearson's R when we calculated Pearson's R by hand. Now, I've used this same data that we used for the correlation PowerPoint for the correlation lecture. This is all the same stuff. So just as a refresher, this is taking the correlation between number of units taken and your sanity levels, where X is the units, Y is the sanity level, and we did each of this. You can look over the correlation video to kind of give yourself a little refresher on this, but essentially we've taken, here's the mean of this column, the mean of this column. These are just, 6, each x value minus the mean of the x value. So 6 minus 13.8, the mean here. 18 minus 13.8 gives us 4.62. 20 minus 13.8 gives us 6.62, etc. For this line here, or for this column here, we're just taking these two numbers and multiplying them to give us this. So negative 7.38 times 2 is negative 14.76. 4.62 times negative 1 is negative 4.62, etc. So these are the things we need to know, the sum of squares for x and y and the sum of squares for x. The only difference is that we removed this last column. It's pretty much all the essentially the same exact chart as it was before, except now we don't have this last column, which is the sum of squares for y. Why is that? Because we don't need it for here. To calculate the slope, the b, so remember our equation is y equals bx plus a. So b is our slope, which is the change of y, and the change in y, which we're going to use the sum of squares for x and y, and divided by the change in x, which is the sum of squares for x. So looking back, again, I'm going through this part quickly because correlation, I've already covered all this information in the correlation video. And correlation, you're going to do that first before you calculate linear regression, as you can tell, because if you calculate linear regression by hand, you need most of the same stuff that you did for calculating correlation by hand. But the sum of squares for x and y is just the sum of this column, which was negative 41. And we're doing the sum of squares for x, and that is 157.84, excuse me, which was the sum of this column. Okay, so to calculate the b, the slope, we just take negative 41, our sum of squares for x and y, divide it by 157.84. So we take negative 41 divided by 157.84, and that gives us a slope of negative 0.26. All right, so we have b. All we need to do now is calculate the y-intercept, which is referred to as a. So to calculate the y-intercept, a is equal to the mean of the values of y minus b, so the slope, times the mean values of x. So again, we have all of this information. The mean values for y is 3, and if you need to go back to the chart to reference it, I can right now. So we found the mean values of y, which is just all of our sanity levels for each participant added together and divided by how many participants, which was 8. That gives us our mean of 3. We need to have our slope, our b, and we've calculated that previously here. And then we need to find the mean values of x, which again is just adding all of our x values together and dividing by 8, the number of x values that there were. So we have all the information we need to calculate the y-intercept. So first, it's the mean of the values of y, which was 3, minus slope times the mean values of x. So I have brackets here to make it easier so we're not getting so confused, but essentially it's 3 minus negative 2.6 times 13.8. Now we need to do multiplication first since it's the order of operations. So the first thing we'll need to do to calculate the y-intercept is multiply our slope times the mean values of x. So we have negative 0.26 times 13.38. That gives us 3.48. Okay. Now that we have b times mx, now we can just take the mean values of y minus that number. So again, the number that we got from multiplying b times the mean values of x, slope times mean values of x, was negative 3.48. And so the mean values of y minus slope times the mean values of x is just 3 minus negative 3.48, which when we subtract a negative number, we are adding it. So we are doing 3 plus 3.48. That gives us our y-intercept, our a, to be equal to 6.48. Cool. Now we have our regression equation. The things we need to calculate are just the slope and the y-intercept, which we've just done. The slope is negative 0.26, that's our b, and our y-intercept, excuse me, our y-intercept a is calculated to be 6.48. So for this linear regression equation, the linear regression equation for that particular example of our correlation as before is y equals negative 0.26x plus 6.48. So we can plug in values for our predictor variable, our x, our units taken, to predict the criterion variable of stress. So what we do is, if there's a student that's taking 16 units, or 17 units, excuse me, we can use this equation to predict what their sanity levels would be. I think I said stress. I meant to say sanity. In fact, I have stress all over this, but it's sanity. But I mean, some could say they're interchangeable with education. But if a student is taking 17 units, we can use this x. Remember, x is our number of units. X is always provided to us. Use this number of 17 to predict our y value. So we're using 17 to predict what their stress or sanity level would be. So y equals negative 0.26 times 17, our x, our provided predictor variable, plus 6.48, our y-intercept. So once we do that, our predicted stress or sanity levels for a student that's taking 17 units using this regression equation is 2.06. So their sanity or stress level would be 2 approximately, but 2.06 to be exact using this equation. Okay. Okay, so group collaboration, I know we can't really do this, but at least as a group, but let's go through this. So the following regression equation of y equals 0.82x plus 0.68. Remember, 0.82 is our slope, our b, and 0.68 is our y-intercept, our a. So we want to use this equation to predict college GPA. So this is, we're predicting something with these values are unknown to us, so this is y, using students' high school GPA, which is x. So the high school GPA is going to be provided to us, and we're going to use this high school GPA to predict what we think their college GPA will be. So we're going to do that. So this first person has a GPA of 2.5 in high school. We have x equals 2.5. Okay, so what do? Well, we just plug it in. So y equals 0.82 times 2.5 plus 0.68. All right, so, oh, I need my handy dandy calculator, which I have charging. So 0.82 times 2.5 equals 2.05, and then we're going to add 0.68. So the predicted college GPA for person number 1 is 2.73. Again, we're just plugging in that 2.5 for x and just calculating y. The next person has a high school GPA of 3.7. So we're going to do the same thing. 0.82 times 3.7 plus 0.68. All right, so let's do it. 0.82 times 3.7 plus 0.68. That second person has a predicted college GPA of 3.714, or just rounding it to 3.71. Third person, they have a high school GPA of 3. So we're going to do 0.82 times 3 plus 0.68. So 0.82 times 3 plus 0.68. Their predicted college GPA, their Y, their criterion variable, is equal to 3.14. They have a high GPA. And finally, the infamous Tammy, her GPA in high school was 0.5. How did she graduate? And now 0.82, again, our slope, times our predictor variable, our X. So 0.82 times 0.5, I got 0.41. And now we're adding our y-intercept of 0.68. Tammy's predicted college GPA is 1.09. So we have 2.73, 3.71, 3.14, and 1.09. Those are the y variables, the criterion predicted variables, predicted, not predictor variables. That's the criterion variables for these four people using this linear regression equation. And it makes sense. We're using high school to predict college GPA because high school comes first, so we have this number. And maybe these are all, you know, fresh going into college, and we want to predict what their college GPA will be. Again, we're taking their cumulative high school GPA, plugging it into this equation, and we have their predicted college GPA. Now, it's predicted. We don't know for certain that this is certainly what they're going to get. But again, linear regression, we're using it to predict. So there's a way to calculate, oh, one thing I should say is that the stronger your relationship between your two variables, so this is relating to Pearson's R. Like I said in the beginning, correlation and linear regression are very closely related. And you can tell that because a lot of the same numbers you need to calculate correlation are the same numbers that you need to calculate linear regression. But I should say that the larger the strength of your correlation, so the larger the number for Pearson's R is, the number itself, not taking into account the direction of it, but the stronger the relationship between the variables are, the more accurate the predictions in your linear regression will be. So if you have a very weak correlation of like 0.01 and you use a linear and you calculate a linear regression equation from that, that prediction might not be that accurate. But if you have, let's say, a perfect correlation, let's say 1.0, R equals 1.0, then that linear correlation, that linear regression that you use to predict is probably going to be pretty damn accurate considering you have a perfect positive correlation. Boom. Okay, so now I can talk about this. So I'm not going to have you guys calculate linear regression by hand, but I will show you guys how to do it in Excel, or at least how to get it set up. So you'll need the data analysis tool pack, which you can use by by adding it to your Excel. Oh my God, by adding it to Excel. So you're going to open up Excel and click on File in the top left corner and go to the bottom where it says Options. Then you're going to click Add-ins. So you're going to come here and you're going to go down to Add-ins. Once you've done that, you're going to click on the bottom where it says Manage, and it's going to say Excel Add-ons. And you want to make sure that is selected and click Go. From there, you're going to check the Data Analysis Tool Pack and the Data and the Analysis Tool Pack VBA, and then click OK. And then boom, you've just added the Data Analysis Tool Pack. If you have Mac, it might be a little different. I used my computer, which is a PC. So if you have Mac, you might have to go through a slightly different process to do so, but you do still have access to the Data Analysis Tool Pack. So now that we've done that, it's really easy to calculate an analysis of regression. So this is where we're taking that null hypothesis test again. So our null hypothesis is saying that the variance in the level of stress, or sanity, it was sanity before and I have stress here, so I apologize for that. but the variance in the level of sanity stress is not related to the changes in the number of units taken. So that's saying there is no, you can't predict stress or sanity from units taken. There's no relationship between these two. And the alternative hypothesis is, of course, saying the opposite, as it always does. The variance in the level of stress or sanity is related to changes in the level of units taken. So that's saying, hey, you can use units to predict your stress or your sanity levels. There is a relationship here, and the changes in one are related to changes in the other. All right, so I have talked about, here's the results. So here, I'll go over what this looks like in Excel. But the number of units taken, analysis of regression was calculated, and we've done it on the next slide. I'll show you here. So here's the numbers once you've calculated linear regression on Excel. Again, I'm not going to ask you to do this, but I'm just wanting to show you. This is what it looks like. So this F, your degrees of freedom, is F16. So I've circled and color coded. So the numbers that are circled are the numbers that are plugged in here. So red circle, red numbers, that's where we got that 1 and 6. Purple circle, purple circle, F is 47.24, 47.24. P is less than 0.05, so we know we have statistical significance because this P value is so incredibly small. And our R squared is equal to 0.89. And this is using the regression equation that we used before. Now, let me go back to this. So the analysis of regression showed, since we have such a low p-value, we reject the null hypothesis. Essentially, we are retaining the alternative hypothesis. And the alternative hypothesis was saying that the number of units taken is related to, it can significantly predict the level of stress or sanity in students. And this is the readout for that. So R squared, I know I kind of glossed over that, and I wanted to go over that right now. R squared refers to the coefficient of determination. This is essentially the proportion of variance. So it's saying that since our R squared value was 0.89, it's saying that 89% of the variability in stress levels, remember the criterion variable, the thing that we're predicting, 89% of the variability, so 89% of the changes in stress level can be explained by the number of units taken, the predictor variable, that X variable. This is pretty damn good. To have 89% of the changes in your sanity or stress levels be attributed to your number of units taken, hey, that's pretty damn good. Hence, I'm not surprised that we have rejected the null hypothesis. So that's all I really have to say about linear regression. Essentially, what I'm going to ask you when it comes to an exam or homework or in-class activities, etc., is one, I want you to know that linear regression is the only statistical test that is used to predict something. So if I'm going to have a question of, ooh, which inferential statistical test would you use? And it has something related to, oh, such and such is being used to predict such and such. Instantly, that word predict is a buzzword for linear regression. So I'm just kind of giving you answers at this point. Linear regression, excuse me, linear regression is really the only statistical test, at least in the sake of our class, that is used to predict something. So if I'm asking you which test would you use, and you see the word predict in the example, you know that's linear regression. It's the only test that does that. Two, the second thing I'm going to ask you about linear regression is going to be similar to how we have our, similar to what this group collaboration was. I'm going to say, oh, you know, I'm going to give you a little example. So the following regression equation is used to predict college GPA using students' high school GPA. Use this equation to predict college GPAs with the given high school GPAs. I'm going to give you, you know, an example of this is what the linear regression is telling us. This y equals 0.82x plus 0.68 is used to predict college GPAs with given high school GPAs. And then I'll provide you like, oh, let's say a high school GPA is 3.7. What's their predicted college GPA? Now, I'm probably not going to use this exact example. In fact, I most definitely will not. But in terms of the questions that I'm going to ask you about linear regression, it's going to be, one, know that it's the only statistical test we cover in this class that's used to predict something. And two, the next thing I'm going to ask you about linear regression is essentially just plugging in numbers to the formula and predicting what that Y criterion variable will be. And that is that. So in terms of the content that we're going to cover in this class, since this semester has been such a mess with COVID-19 taking over all of our lives, this is the last content, this is the last piece of content that we're going to cover. I've had to kind of, since we had that week off, or not off, but since we had a week taken off this semester that gave time for us instructors to kind of transfer our stuff, transition into this online distance learning format, we're not going to be covering chi-square. So I know I've updated the, or I've posted the edited, updated statistics course schedule on Canvas, and you'll see that linear regression is the last thing that we cover. Correlation and linear regression, the last two things that we cover, and that's it. So next week, we're going to have another exam, or we're going to have, exam review, because believe it or not, finals are coming up. So whew, it's been a wild ride. But this, again, is the last thing we'll cover. Hopefully, I tried to organize the class to where near the end, I know that t-tests, be it dependent, independent samples, those can get complicated. And then we add ANOVA onto that, and it's like, holy crap, this is insane. I'm not understanding this. A lot of students have problems with ANOVA, but I tried to end the class, end statistics, on a relatively easier note. I've already hammered in your heads throughout this semester that correlation does not imply causation. So I'm hoping by the time we actually get to correlation, you're like, oh, finally, now I can make sense of all this crap, and boom. So correlation I covered before in a previous video. Linear regression, as I stated here, and you can tell by the numbers we use, is very closely related to correlation, linear regression is. So another thing that I want to tell you is that if I have a question that's like, oh, what's inferential test, or what statistical test is very closely related to linear regression? It's gonna be correlation. Boom shaka. Anyway, so if you have any questions relating to this material or anything going on in the class, be it content related or what the hell's going on related, or questions about just the logistics of the exam or grading, always shoot me an email if you have a question. I'm happy to answer them. And it's been a hell of a semester, and I apologize that it had to turn out this way. Didn't really have much choice or control over the matter, but I hope that all of you guys are staying relatively happy, relatively sane. We can use a linear regression to predict that perhaps, but I hope you guys are all doing well, and I hope to one day see you again if we're ever able to leave our houses again. But thank you.